What's going on? Alright, so this is the model that I created for homework number 2. As you can see, I have my light here to kind of shine. I had to use my closet as a way, so I had a kind of a keychain plus a watch on there to kind of, see some more prominent results. As you can see, there's 2 rubber bands here to 1 rubber band right there, and then this one has 3 of them here. And so, overall, so this is kind of the model that I created to kind of represent this problem and gather data. So I wrote down the data here on a piece of paper. Let me just bring back everything. So I recorded it here. So kind of length across the top, 8, and then when you kind of just go down the middle after measuring 3 centimeters on one side. I measured in centimeters. My ruler's in inches, but I went on to an online converter to convert them to inches. And so you get the weight, and so the overall weight of this was 0.305 kilograms, and so I just times that by the gravitational constant, so you get 2.99 newtons. And then after that, I took that into Hooke's law, and then the newtons times the stretched length, and divided that and got, my bad, sorry, these numbers, which are my Hooke's thing. Kind of had a brain fart right there. So just mounting that back up there. So as you saw, here's me I'm just going through some of the problems. Let me just set that up. So as you can see, just kind of going through the problem statement here. It says, determine the stretch in the springs AC and AB for equilibrium of the 0.305 kilogram weight. The springs are in an equilibrium position. So I took the problem that was mentioned and I just kind of applied my own numbers to it. And so as you can see here, I did kind of my drawing, so I put the spring constants from there onto the drawing, and then there's, kind of the weight at the bottom. And so here's my free body diagram, kind of force AC, force AB, and then force AD heading downwards. And so, here's some of the methods and the calculations, assuming that gravity is a constant, of course. One assumption is that the springs had no form or kind of deformation to them, that they were, kind of working the way they should have been. And then we used Hooke's law, and, kind of did that. And then, the kind of equilibrium where, Fy, sigma Fy and sigma Fx equals 0, and the totality of them equaling 0, and then use some trigonometry to figure some stuff out. So, as you can see, you set that FAD, since it's heading directly down, you can just kind of count this in a 2D plane as a y-axis. And so you can just set that equal to your weight. And so when you do that, you get your 2.99 newtons, and that's your force in the, down direction. Even though it's a positive number here, I just kind of kept it positive even though it's oriented in the negative direction, just for ease. So just going back to that, you could just plug that number back in, times S, and then boom. You can figure out kind of, what's your change in your spring length in centimeters, so I got a 5.1 C. And so going back to the free body diagram, I didn't mention this earlier, but it's very important to know, but we have our angles alpha and theta that we are, you can't see it yet, theta, that we are solving for. And so we just use some trig, since we do know the heights and the dimensions of the triangle, just not the angles, as you can see there listed. All we have to do is just plug it into the tangent formula to find theta, and we do so. We get for theta we get 47.5 degrees, and alpha we get 63.4. And so we just kind of plug these into our summation formulas, as you can see there. So it's, you know, FAC, and so they equal 0, and then you just kind of plug in your numbers, and then you simplify them, and you just kind of leave that for X, but when you go to FY, you can do a little more simplification because you have that FAD, which is the weight, and so then you can set the equation equal to the weight. It's kind of like scrunched up there. I was kind of pushing for space. And so, you know, going there, you know, just kind of simplify your numbers, and then as you can see, I put this actually in a system of equations. It may not be immediately apparent. And to get rid of one of our variables, all I had to do was just times it by 2, and so that they cancel out. So that I was just stuck with my FD, my FAB variable. And so you just add them together, set it equal to the weight, and then boom, you get your second force. And so with FAB, you know, KAS, you just kind of use Hooke's law and figure out the distance, and there it is. And so I just kind of repeat the process for FAC to find the distance. And, you know, there you have it. That's the first part of the question. So going kind of back to this very same question, just kind of a different approach on the worksheet, the hard copy homework. He asked, you know, what's the unstretched length of spring AB is 3.81 centimeters. If the block is held in the equilibrium position, you know, determine the mass of the block, or whatever the weight you had. As you already know, it was like kind of a keychain and a watch. So even though we know the keychain and the watch prior, we're supposed to, in this scenario, act like we don't know. However, so we still have a lot of our experimental data, and so that a lot of the same values will be present. It's a very similar free body diagram. However, we are looking at the theta. We brought the theta outside. So this theta becomes, you know, that theta, you know, parallelogram law, and then, you know, etc., etc. So it's not really all that different. Like I said before, this one's more kind of reliant on the distances and everything, and Hooke's law will be present again. So, you know, it says, you know, find the force of AC. So that's this first one, A to C. Sorry, that's a little small, but the A is right there. So, you know, so we just take our distance here, and then minus our unstretched distance, which we found, you know, just kind of measuring out the rubber band in its natural state, unflexed, times our spring constant that we calculated based off of experimental data, and then boom, we get, you know, our force. And then you use the kind of the lengths of the triangle to use that tangent formula again to find out, you know, these angles, and they're pretty much the very same angles that we had before, just, you know, kind of flipped. And so it's just essentially the same idea. You just put them into kind of an equation, and you just solve for one variable this time. So you get 0.78 Newton. Because we had the FC figured out from before, so we could just plug that back into the equation and figure out FAB. And so knowing that, through our y variable, since FAD only acts in the y-axis, or in, you know, in this kind of our, it heads in the downward direction, which in this case is our y-axis. You know, we could just plug back into the equations, set it equal to that negative FAD, and so just solving it, FAD, we get our weight, and then FAD is equal to the weight. That's that. And so when you divide that weight by a gravitational constant of 9.81, we get our weight of 1.68 kilograms. As you can see, I did miscalculate something wrong in our experimental data configurations. However, I do believe the math is right, so it was just an error on my part.